Okay, everybody. It's 2 p.m. at least in this side of the world. Thank you again for all of you at still with the school. We even noted that more people have been joined to the Slack even at the last day. Well, today, last day of the school. So that's incredible. And now we will have the lecture by Claudia Svelitz. Sorry if I pronounce it wrong.
That's fine.
Thank you. I should use the last two letters. So this is in principle our last presentation, our last lecture of this school. So I just want to profit to thank you everybody that is still there. Obviously, thank you, Claudia, to be here with us, and to everybody to to commit to all this effort, and have been great to be with you guys. So please, Claudia, the floor is yours, and thank you again.
Thank you for the kind introduction, and hello everyone for the last afternoon lecture of the summer school. I'm going to talk to you about validation and optimization of machine learning models and about regression models. And maybe a bit of background about myself. I am a chemist by training, analytical chemist, so I come from spectroscopy and have been doing statistical data analysis, mostly of spectroscopic data, for some 15 to 20 years by now. And I came to this summer school via the carpentry, so I'm a bit foreign to astrophysics. And I'm also foreign to Python because I usually work in R. And that's why I'm gonna do basically the presentation. But as soon as the questions get deeper into Python, Benson will help me out, who's kindly around on the Slack. So with that, let's have a look at the agenda for this afternoon. I'll give a very brief introduction into what verification and validation means. Oh, yeah. We'll then look more in detail into some figures of merit, which Martino has already mentioned this morning. Then into plans, how to arrange your data for verification purposes, and cover in more detail one very important technique, which is cross-validation under the heading of resampling. Have a glance into questions of model stability, also that came up in the morning already, and a quick glance into sample size planning before we look at the larger picture of validation, and then look into model optimization and hyperparameter tuning, first with classification, and then we're gonna do a little glimpse into regression, using also the question of hyperparameter tuning as our, let's say, application.
Now, Claudia, sorry to interrupt you.
Yes.
Sorry, but you have maybe the window on the right, which is maybe the faces of the Zoom is blocking your table of content.
Oh, I'm sorry.
You want to hide that one? Yes.
I want to hide that one. There we go.
Perfect. It. Thank you for
maybe here. Sorry. Okay. So there's a little bit of differences in terminology between different fields in analytical chemistry and in many engineering fields. We're using the term verification to mean making sure that is measuring and proving, showing that the model we have, or more general, the predictive method we have, meets the specifications, as in you have a sheet with a list of specifications that your model is supposed to meet. And then validation is the larger picture of making sure that the model meets actually the application needs. And this is a difference. Most what we're doing in geometrics, but in general also in machine learning, even though we call it model validation quite frequently, is typically more like a verification step than the large validation. And what we want to do is we want to characterize our model by measuring its predictive performance. There are other aspects that enter both verification and even more validation. But this is for this afternoon the bottom line of what validation and verification is going to mean to us. Why is this important? This is an example from a paper in Nature 10 years ago that was concerned with reproducibility of medical studies. And basically, they did a literature search and estimate that some 150,000 papers are out that claim to have found some kind of biomarker for some kind of disease, which is very similar in a way to, well, it's a wet lab equivalent to us saying that we have a machine learning model that can detect cancer or whatsoever. And in the end of those 150,000 papers that claim basically thousands of biomarkers of some kind of importance, in the end, only about 100 of them made it into routine clinical use. And this is not because the clinicians are somehow reluctant to use more biomarkers, but because they turned out not to be reliable. And exactly that is what validation is supposed to catch, basically. Verification and validation are about making sure that your model will actually perform with a sensible accuracy. In general, we can say that there are 3 ingredients to verification and validation testing, as it is also called. The main ingredient, of course, is the model, which we study in verification and validation. And Martino has already said this morning, this is kind of treated as a black box. So we're taking the model and we're taking cases, that's input data, X data, and the model then takes this case and produces a prediction, which for classification will be maybe class label, maybe also class membership as a score or as a probability, or in regression, a continuous output. And the second ingredient is a figure of, or several figures of merit, that is a way to measure the performance or particular aspects of performance. And there's not one figure of merit that is kind of the one we always use. There are many of them, ranging from overall accuracy, sensitivity, specificities, predictive value, which are all classification figures of merit, or mean squared errors, root mean squared error, and so on for regression. And the third ingredient is that we need to have a plan how to get those test cases, because it's actually not as easy as the morning tutorial did it, and just, setting aside a random fraction of your data. We need to think a bit harder what exactly are the cases that we want to test. And one thing we know already, way back, maybe close to 100 years back, when there was, the univariate line of best fit was fitted. Back then, the residuals or auto prediction or training error was actually sufficient to determine whether your model does well or not. With models with large numbers or high degrees of freedom, large complexity, this is not sufficient. So we need to test on independent data. You've also heard that this morning already. And so the third part will be looking into how do we get basically the cases we need in order to test what can we do in this respect, and what are the particularities of these different plans that are around. Let's start with the figures of merit. You've already seen in the morning lecture things like accuracy, and you've also seen the so-called confusion matrix. The confusion matrix tabulates basically the reference information about our test cases against the prediction for a classifier. So in this example here, I have 3 classes, A, B, C, and in order to have them easier referred to, I capitalized the reference one, although you can use the same labels here. And then from this confusion matrix here, which you've plotted in the morning already, we look at certain fractions and proportions of certain parts of these. So, for example, sensitivity, we can describe sensitivity for class A as those cases that were correctly found as class A, that also actually belong to class A, that's why it's correctly found, put into proportion to the total number of truly, that is reference, class A cases, which would be the marked row here. In contrast to that, there is also the specificity, which does the opposite. It looks at which cases that actually do not belong to class A, those down here, were also found to not belong to class A. And I need to tell on the Slack. Okay, excuse me. There's another important pair of proportions here, which are called the predictive values. And they, in contrast to looking at fractions of the cases that truly belong to the class or truly do not belong to the class, they look at fractions of the cases that were predicted to belong to the class or to belong not to the class. And again, it's the correct fractions among those. So what we can say is that these different figures of merit answer certain types of questions about our model. Sensitivity, as I said, of all truly class A cases, which fraction is correctly recognized as class A. This is also called recall. Specificity, the opposite, those that truly do not belong to class A, which fraction thereof was correctly predicted. Positive predictive value is also called precision. Although, careful here, there's a bit of a mess with the terminology, because precision may also mean low random error. So you need to be very careful when you use the term precision, which of the meanings you refer to. Anyways, precision or positive predictive value means of all cases that are predicted to belong to class A, which fraction does truly belong to class A. And usually, most users are more interested in the predictive values than in sensitivity and specificity. Because that's, well, if you go for a COVID test and get it positive, you want to know what the probability is that this result is correct. You're not necessarily interested how well technical more technical characteristics like sensitivity and specificity, which do not include your prior probability of having COVID, are. In order to get a bit more of a grasp and feeling about this, let's do an exercise. And I would kindly ask you to, open a new notebook where we kind of get warmed up for the afternoon. And so let's start actually with a COVID self-test. The COVID self-test I did this morning told me in its little sheet some results they had on the validation of this test, actually. So where we have a little table where, again, we have the reference, that's the PCR. And this can be positive. And they had 103 participants that were positive according to PCR and also recognized by the self-test. They had another 5 of the PCR positive that were not recognized by the self-test. And they had 1 PCR negative that was unfortunately thought to be positive by the self-test, but 114 further participants of the test study were correctly recognized as not having COVID. So let's start by making such a little matrix. I'm sorry. I'm sorry, the screen where I have my notes went black. So I have to have it restarted. So we're gonna use NumPy and we're gonna call it fusion matrix, little MP array of 103 and 5 and 1 and 114 cases. There we go. And we can then calculate sensitivity and specificity according to the proportions that I showed in the slides, as because we can calculate in a vectorized fashion, we can use the diagonal elements, which are the 103 and 114. That is the 2 correct results here. And we have to divide this by the row-wise sums. That is, we sum the confusion matrix along axis 1 and can then. Oh, someone is asking whether confusion matrix is a NumPy library or a function. No, the confusion matrix here is the name of the variable where I stored the matrix in with the test results that I typed off the sheet, basically. So we can print our sensitivity and specificity, and we see that the test was found to have 95% sensitivity and 99% specificity, which so far looks really great. Now let's have a look at the positive and negative predictive value according to what the drawing about the calculation said. So this is basically, again, the diagonal of the confusion matrix. That is our two correct cells of the table divided now, now divided again by the sum, but now of the columns. So it's axis 0 here. And again, we can print them. And wow, they are just looking great like the others. But Martino already warned you this morning that actually we need to take into account the probability that you really do have COVID. And what you see here is something that we have both in machine learning as well as in, for example, the development of medical tests. The validation study for those tests are set up in a way that we specify we want to test 108 patients that are positive according to the PCR and 115 that are negative according to the PCR. But the fraction 108 to 114, that is about 50-50, doesn't have anything to do with the frequency of COVID positive samples that you meet in the application. And this is what we are going to need here. So let's do back of the envelope calculation, where I am currently. The incidence is about 11.6 cases per 100K inhabitants and week. So we can now what we need is the probability to meet a truly positive COVID sample. We can also call it incidence, and I will actually divide those 11.6 cases already by 100,000 because it's per 100,000 inhabitants. And I will divide it by 7 days per week. So I do have a daily incidence, which is corresponds to something from which we can calculate the probability. In order to get this probability, we need to think that, well, let's say someone infected will be running around maybe approximately 3 days without being detected before they're isolated. After that, they're not in the population for the self-test anymore. And we do have a dark figure that's about as large as the incidence again. But those people are running around and are positive or in fact contagious, sorry, for about 8 days. That's what I gathered from the newspapers. So this means we have a probability when someone comes along at our new test center and does a test, or someone does a self-test of maybe something like 0.00018 of this sample being actually positive. We can also express this, that 1 in almost 5,500 people we could meet today would be expected to be truly positive. Now, what we next need to do is we need to basically scale the rows of our confusion matrix according to this probability. So we first need to basically normalize it so that each row corresponds to the fractions of tests in that row. That is, we have a row sum of 1 here and a row sum of 1 here. And then from that on, we can enter with our true positive probability. So let's start with that. And open a new variable, confusion matrix incidence corrected as confusion matrix. So we want to correct for that slight deviation between 115 and 108 patients in the rows. So again, confusion matrix, we need again the row sum. And now we also need to keep the dimension. We can print it. So we can just have a quick check. Yes, the row sums are both 1 as we needed. And now we need, we have a question in the Slack whether the incident isn't computed from the test results, and wouldn't it be problematic to use the result back to check the test's correctness? This would be true, but the test results from which the incidence is computed are actually the PCR results. So not the results of our self-test, but of the proper approved lab test. So this is basically what we're looking at, is this kind of self-test you can do, which would then, if it were positive, be a reason to go to the test center and get one of the PCR tests. So the PCR test, that is the result from which our incidence is calculated, and also where our rows come from. That's the that is actually independent of what our little self-test says here. But yes, you need to be careful to have the correct tests there. And in general, this is something you try to look up in the epidemiologic literature. And it's very hard to get these numbers actually for various application scenarios. So let's go on. And scale the first row, with the probability we estimated above. and the second row with 1 minus this probability. And then, of course, we want to print the corrected result again. So now the numbers are well, this is almost 1 and the others are almost 0. But let's look what our predictive values do now. And I'm just going to copy from above here, but leave that there so we do have kind of a log of what we were doing in this session. Okay, sorry. Of course, we need to use here our newly corrected confusion matrices. What we see here is now that our positive predictive value, that is the probability of actually being COVID positive according to the PCR test, when a self-test was positive, right here for the situation where I am, something like 2%. 1 in 51 people who get a positive test result here at the moment are actually truly positive. So, checking the Slack. With that, let's have a look at our figures of merit again. In general, we can say that any kind of proportion here that summarizes more than one row of the confusion matrix means that you need to think hard whether the relative counts in your rows are correct for your application scenario. So to come back to that, they're well-known, widely used, but we need to be careful because sensitivity and specificity are easy to measure, but not that relevant for the application usually, whereas the predictive values are highly relevant, but difficult to measure because we always need to know those relative class frequencies and then need to weight accordingly. There are even more figures of merit. You can do statistical correction for the chance of just by guessing being correct. Maybe the most well-known is called kappa, but you can do that with basically all kinds of figures of merit. There are 2 more figures of merit that I'd like to mention here because they are very handy in judging what your method is doing, because as we've seen, very nice looking sensitivity and specificity actually may still lead to a situation where the positive predictive value or the negative predictive value, depending on how you set up the whole thing, your test, is actually not that great. And another pair of figures of merit that are independent, that are independent of the relevance, the incidence or prevalence, depending on what kind of test you're looking at, are called positive and negative likelihood ratio. As you can see here, they're computed from sensitivity and specificity. And they give us a number that is related to the information we gain when a test result comes out as positive or as negative. So let's compute them again, also here for our COVID test. Likelihood ratio positive is sensitivity divided by 1 minus specificity. And our negative is basically symmetric the other way around. Specificity divided by 1 minus sensitivity. And we can print them. And what we see here, well, actually, if the test comes out positive, this test is set up in a way that we have a very good information gain, actually. It's 2 orders of magnitude that the odds increase here. Negative result doesn't give that much information, only a factor of 20 in information gain. But this still means, let me go back to our tests, that we have, even though we are still in a situation where only 1, or for every 50 that get a false positive self-test, only 1 gets a true positive self-test, because right now the odds of actually having contracted COVID are so low. I'm checking the Slack. Thank you. Now, there's one more, let's say, one more characteristic of these proportions I want to make you aware of. From a statistical point of view, we can describe our testing procedure as a Bernoulli trial. That means we're doing a random experiment where, with a certain kind of probability, the outcome will be positive. That is any of our classes, or the class to which our figure of merit belongs, basically. And this means that we have a binomial distribution, which I have here in this 3D-ish picture, depicted in the axis going to the back. So along this axis, that is for a known true sensitivity, we can easily compute what kind of distribution for test results we would expect. And what we now want to do is saying that, given that we did observe this many cases correctly recognized out of so many tested cases, what's actually the probability? And this part here is exactly what I depicted here as well. So what's our probability estimate? That is what we call here, for example, the sensitivity. And can we have maybe a measure of how certain we are about this? That is, can we have a confidence interval? And we can actually. There's a normal approximation, which you can use if you have very large numbers of tested cases, and also sensitivity or any other figure of any other of the proportions not being too close to 0 or 1. But actually, we can just have a proper confidence interval calculation. And this here, what, for example, if we look into AstroPy stats, we can use function, sorry, norm conf interval with our confusion matrix. And if we're going for sensitivity, that's the very first row and column as the number of successes, and the number of trials is again the sum, sorry, of the confusion matrix of our first row. And we can then give an additional parameter that tells us, because there are different approximations, which approximation or which method to calculate the confidence interval we're going to use. So I'm going to use the flat one here. And this means our sensitivity, which we estimated before, sorry, I'm going to print that as well, which we estimated to be 95.3 blah 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 %. That's actually not that well known, but we think it's between, let's call it 92.4 or 92 and 97% actually, somewhere. What we can do with these confidence intervals, which is also important for planning our tests, is we can have a look actually at the width of such confidence intervals, sorry, depending on the number of cases we have in the denominator of our proportion and on the observed proportion. And what you can see here is that if you're around with small sample sizes like we typically have, let's say in medical diagnostics, those confidence intervals are actually really, really wide. And this is one of the drawbacks actually of the proportions. They're very intuitive in their meaning, but they do have this huge variance, which is quite a bad thing. There was already this morning a question whether there will be some more information available besides just the case being on the one or on the other side of the class boundary in the support vector machine. And actually this is the case for many, if not almost all classifiers that are around. You can have some kind of scores that give you kind of a continuous measure on how far away and on which side of the class boundary you are. The interesting thing is that you can use this fact, this continuous classification result, and basically move your boundary along those scores. So basically shift your boundary a little bit. And if you then put of the resulting set of classifiers, specificity against sensitivity, or 1 minus specificity is also often used, and it's flipped basically, then you get a curve here, which is called the receiver operating characteristic. And you can select a working point for your classifier that is basically a cutoff, the threshold that defines where on this direction of belonging more or less to one class, where on this line your actually cutoff is done. And this is important because for different applications you have different needs. For example, the COVID test we have here, because of the very low probability that someone who's testing themselves is actually positive, what we need is a very high specificity. And sensitivity may be better traded off a little bit for better specificity here in order not to have 500 false positives for each one true positive. Over here on the right side, you again see those likelihood ratios, LR pos and neg, that tell us the information gain. So you can use them as a coordinate system here as well. I've already mentioned this kind of shifting of the line. This is something we very often do in hyperparameter tuning, because hyperparameters usually steer our model, and many of them allow us to, well, optimize the model in a continuous fashion. Now, let's have a look what our proportions are doing here. So we have some kind of hyperparameter that at the initial setting, hyperparameter along the x-axis, leads to some kind of performance, and this is the classifier we get, and here's our test case. Now we do something to the hyperparameter, so the class boundary moves, our case stays where it is, but see what happens. Our proportion just stayed exactly the same, even though our class boundary moved now very close to our test case here. And now we move it a tiny little bit, and we get a huge drop in our figure of merit, in our proportion. And then again, nothing happens. So this is not exactly what we want for something, for a figure of merit that we want to use as the target for an optimization. Because for optimization, we would want to have a target functional that continuously penalizes the closeness to the class boundary, and that continuously reacts to changes in our model, so that if we have a slight deterioration, we would get a slight drop in measured performance, but not nothing or a whole lot of a drop. And in addition, well, for optimization, we'd like to have it optimal, exactly 1, and this should also coincide with the best classifier. So here's a more continuous behavior. And there are actually figures of merit that do have these characteristics, and they're called strictly proper scoring rules. The bad news is our proportions are not even proper, not to speak of strictly proper scoring rules. So if you optimize your models, give a serious thought whether you can't move to a proper scoring rule, because the whole optimization will be easier and more stable with that. You may then afterwards calculate as many proportions as you like in order to have easy communication to the stakeholders of your application. But for the optimization, this is, well, strictly proper scoring rules are guaranteed to be basically well behaved. I'll jump for a second to regression. And in regression, maybe the two most important figures of merit are the mean squared error, which is the loss function behind Gaussian least squares and tons of other least squares methods, and then the root thereof, the root mean squared error. They do penalize large deviations compared to many small deviations. If you have few that really stick out, you will get a very high root mean squared error or mean squared error. They're basically, well, what the name says. What we do is we compute the deviation between the prediction and our reference value. We square it, we take the average of this, and in case of the root mean squared error, we then take the root. The reason for that is that in this fashion, we get a figure of merit that is in the same scale and unit as our y. So for example, if y is an analyte concentration, then our root mean squared error is also a concentration and in the same, well, really on the same scale. The mean squared error, on the other hand, has the nice mathematical property that we can decompose it into the square of a systematic deviation, that's the bias, and the variance, which are, in a sense, the square of the random deviations we have. Now, I introduced the mean squared error at this point because there's Briar score, and Briar score is the mean squared error applied to classification. So what we take here is a classifier that doesn't output labels ABC, but instead has as output the probability of the case belonging to class A. And this is in the interval of 0 to 1. And we can then here calculate something like the mean squared error and use this. And Briar score is one of the strictly proper scoring rules. So this is one possibility how you can get your optimization work better, possibly. To sum up the figures of merit part, there are many different ones. You have to choose the relevant ones, and which are relevant will depend on your application. You will usually, for classification at least, use several of them and look at them together. Figures of merit are measured. That's basically what we do in validation and verification. And this means they are subject to bias and variance like any other measurement. We've been looking into the variance, that is the random uncertainty already with our confidence interval. Regression figures of merit are usually more well behaved. On the other hand, we can't do these back of the envelope guesstimate for example, required sample size, as we can do for the classification proportions. And again, use the strictly proper scoring rules for optimization. This can't be said too often. Now, the second ingredient I told you is the scheme, the plan, how we get the samples that we actually want to test. And the one really crucial thing here is, in order to get a fair estimate on how our model will perform for new unknown data, we must be sure that the data we test with is actually unknown. And in statistical terminology, unknown is called independent. Why am I emphasizing this so much? We have actually in practice very frequently the situation that our data is structured and not only according to the classes that we want to predict or to the continuous metric that we want to predict in the regression, but there's all kinds of clusters. For example, we may have repeated measurements that are more similar to each other than to repetition that was not done of the same physical specimen, or we have repeated measurements or different measurements taken of one and the same patient, and so on and so forth. So this is this clustering, which is also called hierarchical data. Or if you think about the factors behind this, you will find 1 to n relationships. And statisticians call it nesting of factors. All these mean the same, that we do have kind of structure where certain parts of the data are more similar to each other because they belong to certain groups. This is very common. And it's also quite common to have spatial or temporal relationships, correlation, meaning samples that come from close by, either in space or in time, are more similar than samples that come from further apart. To give you an example, Martino and Benson kindly provided me with samples of digits written by them. You see them up here. And I'm sure if I show you pretty much any of those numbers, even if they used the same pen, which they didn't, for many, you could correctly say who actually wrote this number. And that's always a very bad sign. It starts with the 8 being either open down here or up here, the 9 having a bit of a curl or being bent in the other direction, and so on. And this means if we have repetitions in our digit data set, then the classifier may learn that things like this are a 7 And it's very easy to predict for them that this is a 7 because it's so similar to those two 7s. But if they've never seen the digits from the other person and they get the 7 like this, it may not be so easy because these 7s have the curvature here a little bit differently. So the conclusion here would be that if there are actually several digits in our digit data set coming from the same writer, that maybe we should exclude all of the same writer's digits and from training if we want to test them. That is, we do not leave one digit out or leave k digits out. We do leave one or more writers out. And at that point, I think it's good to have a quick look what's actually the case with the digits data set. So let's check again. We need to import the node digits. And digits, and then we'll look at the digits description again. You've read that before, right? And I want to draw your attention to this little sentence somewhere hidden down here, and you've seen it before. I thought, oh, that's all okay. But actually, this is the case here. We have many digits, but the whole data set came only from 43 people. They were actually divided into 30 training sets and 13 test set writers. Knowing this, there's two consequences. First consequence, if we go and calculate the confidence interval for the sensitivity from that test set of 13 writers, we better put the 13 as the sample size on which the confidence interval calculation is based on, unless we can show that it doesn't matter, which is difficult. What is even more difficult is that, unfortunately, the scikit-learn version here didn't record what the patients are, the writers are. So you really couldn't do anything else, but what you did in the morning, that is to split randomly digits. But those very, very good recognition results you saw, very close to 100% correct, may in fact be coming from other digits of that same writer being in the training data set. And something happened here that is really, really bad, and that would be totally upsetting if it happens in your research. And that is that this crucial information was lost. So we have a potentially important factor, but we cannot recover it. If you want to dive into the digits data set, you can go to the MNIST database, and there get versions where they're still not recording who wrote which of the digits, but at least you have a training and test set that is divided, as it says here, into 30 training and 13 test writers. I'm not gonna show this because time is getting on. But scikit-learn actually gives you the possibility, when you set up a cross-validation or the splitting, to split according to some grouping variable, such as the writer, if you have it, of course. With that, let's look a bit further into what else we need as ingredients into our plan to get the test cases. In a general way, we can say that there are different kinds of test samples, and from these we can compute different kinds of performance measures. And that's kind of independent of what the figure of merit is. pretty much for all of them, you can calculate all the figures of merit that we've been discussing before. So easiest, we're taking our training samples and look what the performance for the training samples is. What we get there are basically measuring, what we're doing there is that we measure the goodness of fit of our model. Basically, that's what's called residuals in statistics. Unfortunately, it does not guard against overfit because it's measuring how close we get to the training cases. If we want to measure generalization error, that is the performance for unknown cases, what we need are, as I said, statistically independent samples. We can use, for example, resampling or a test set that was measured even at the same time as the training set, but was kept separate even before the training set was ever given to someone to model. We can go on and measure further cases that are independent even in other fashion. For example, it's usually important to predict what the future performance is, because usually you get your training cases, measure them at some point, then you model, and then you ship your model or deploy it. And then the application use will be that new cases are measured later on and then predicted. But possibly our measurement system has a drift. So it may be important to measure how long in future we can use our model, and when do we need to gather new training data in order to maintain our model. Resampling, cross-validation, takes care of the generalization error level of independence. And the idea behind this is basically that we never have sufficient number of cases, because if we had, we would usually want to have a more complex model that models a few more details, and then again we would need more samples. There are some rules of thumb that tell us how many samples we actually need, and that's for linear models, something like 5 cases per variant, that's feature and class, or analyte, or Y column for regression. Basically, we can say that the model quality will depend on the ratio between number of training cases and degrees of freedom or complexity. And so, of course, we want to use all our cases for training somehow. And we want to know how good our model works. We want to know whether it's stable, and we want to know how good it's, well, we also want a precise estimate, precise now in the sense of low uncertainty of our figure of merit. If our confidence interval goes from 30 to 100%, so possibly like guessing to perfect, no one's going to be no one's going to be happy with that, because you can't conclude anything from that. So we also need a sufficient number of cases in testing. And one difference between testing and training is just, whereas we can adapt our modeling strategy to having few training cases only, by actually doing, for example, more heavy regularization of the model. This is not possible for testing. The quality of our test results will always depend on the absolute number of cases we had for testing. And some years ago, I've done for the medical applications, I was involved with a kind of rule of thumb based on the graphs I've shown you before, that basically told me that you really don't want to start doing things if your number of test cases, test sample size is below 140, or maybe in some cases you get away with below 100. We usually have the medical cooperation partners telling us something like we should do with 10 cases. There's a whole lot of different validation schemes or plans, not only the training error read here and the independent test set over here, but sorry, fortunately you will only need very few of them in practice, and these are the ones that are cross-validation, what we're looking at next, holdout or independent test sets, and the validation study. And the specialty with this holdout is that it's somewhere in between resampling and a validation study, and where it is depends very much on the particular circumstances, how it was set up. And because I'm running out of time, I'm sorry, I will skip these slides, but you can review them at your leisure later on. I brought you a checklist of things that you should think whether they apply to your application and modeling whenever you do validation. The first, I've not been talking about that, but I want to mention it, is randomize the order of your measurements whenever this is possible. This helps you to detect if there's a drift in the system in some kind of way. If you measure them somehow in an ordered fashion and there is a drift, you're never going to know whether it was the drift that you base your classification on or not. Again, for independence, split at the highest level in your data structure or sample hierarchy. For me, that would be, for example, patients or cell lines. But it's also influencing factors on your measurement instrument, possibly day of measurement, before or after new calibration, things like that. You need to check and beware of that. If your data analysis includes a pipeline, we will see one later on, then you need to split your test set off before the first step that involves more than one case. That is the rows of more than one case in your data matrix. Martino already told you that if we use the results of our testing in order to choose which model out of a set of models that is which we want to use, that is in order to auto-tune or optimize our model, then we need an additional set to measure the performance of the final tuned model. And this can easily mean that you will need very large sample sizes. And therefore, it can be good, especially if you're very limited in the number of cases you can get. It's very good if you know your model well and can basically decide the hyperparameters from your knowledge of the model together with your knowledge of the application and the data you have. It's extremely important for testing that your reference labels must be independent of the cases. That's exactly the question that we had before in the Slack. If that incidence were determined from the kind of test we were using, then we would create basically something like a self-fulfilling prophecy, which would lead to bias in our validation results. So the references must be independent for testing. This is not the case for training, and it's actually sometimes done that techniques like, for example, a cluster analysis is used to have a very fast assignment of labels. For training cases, that's fine. There's even an official name for techniques that use this. It's called semi-supervised learning. But you can never use semi-supervised learning generated labels for any kind of generalization error estimate. And of course, you need to make sure that your labeling procedure does also not distort in other ways the difficulty of your test cases. For example, I once came across a data set, again, medical, where because doctors would not always agree on what exactly was the disease status, all cases where the doctors didn't agree were excluded. And the result was that there was an extremely easy data set. But of course, this was of no relevance for the application because, well, no doctor worries about the textbook clear case. They all worry about the complicated ones, and they have been excluded. And then last but not least, make sure your code is correct. Let's look at resampling. This is one of the techniques in general in statistics that we can use when we want to look at the uncertainty, random uncertainty of what we are doing. This is similar to back in your first undergrad year in the lab. You probably somewhere did take repeated measurements of something and then calculated uncertainty based on the differences you had there. And what you do here in the statistical terminology is you have a population and you draw different samples from that, calculate your, in our case, figure of merit, and then compare the resulting figure of merit for each of those samples. But as I told you, samples are scarce and expensive, always, with the exception of maybe Facebook users or Google users. There are billions of them. So we have one sample, and that one sample is usually already too small, not sufficient numbers. So what we do is, instead of taking more samples that we can't afford, we simulate this process of sampling by so-called subsampling. That is, we draw new samples from our blue sample. And we claim that these subsamples are approximations of real samples that we cannot afford to get. There's a second point of view on what these subsamples are. And that's basically starting saying, well, this is not a very good approximation, at least not if we draw, as we do in let's say, tenfold cross-validation. Each of the subsamples will have 90% of the cases of the sample. So they're really not very different. So they're kind of, from the other point of view, you can say that these kinds of subsamples are perturbed versions of our blue sample. And we're going to use that point of view as well. Now, cross-validation is such a subsampling procedure where we draw in a certain systematic fashion without replacement. So let's say we have 6 cases in our data set, and we decide to do what is called k-fold cross-validation, with k equals 3, that is 3-fold, meaning that 1/3 of our samples, that's 2 out of 6, should be reserved for testing, and the other 4 should be taken for training. And now we do this in a fashion that we have 1/3 tested with one model, then we train another model where we leave another 1/3 of our cases out, and finally a 3rd model where the last 1/3 is left out. So in the end, each of the cases is left out exactly once. Usually this is done in a fashion that we assign randomly which of our cases end up in which of the folds. So we have 2 equivalent, or the left and the right picture here are illustrations of equivalent situation. I just reordered them so it's easier to see here how we have this third situation. We can, of course, do this again, now with a different random assignment into those thirds. So whereas here, case number 1 was left out together with case number 3, here it's left out together with case number 6. These are called repetitions or iterations, and we can do them with k-fold or leave n out cross-validation, which is equivalent. So in our case, with n equals 6, k equals 3, threefold, or leave 2 out are equivalent, are the same, not even equivalent, the same. There's one exception: leave 1 out cannot be iterated, and that's a reason, a perfectly fine reason for never doing leave 1 out cross-validation if you can avoid it. Because these iterations help us, as we'll see in a few slides. First, there's some assumptions behind this kind of validation procedure. So as I said, we're taking our 2/3 that were assigned to the training subset, and we build a model. I call this a surrogate model in order to have a different term for that, to distinguish it from the final model, which uses all 6 of the training cases, all 6 of our cases for training, sorry. But then there wouldn't be any test cases left. So we have this surrogate model, and those 2 cases here, 4 and 5, were left out. So we predict them in order to get them as independent tests. Then we go on and on and on. In the end, we have 6 different surrogate models. Now, the first assumption we do is that those surrogate models are equivalent to the one model that we get out of training with all 6 cases. We have a somewhat weaker assumption that, well, maybe that's not quite true, as we will see. But at least the surrogate models among themselves are equivalent, which is why we're allowed to pool all those predictions together and calculate one figure of merit from that whole bunch of predictions. The first assumption is actually regularly violated because we have only fewer cases here in our training for all of the surrogate models compared to the final model. The surrogate models are on average a bit worse than the final model. So our test results will look a bit pessimistic. And that's why resampling validation, as long as you manage to get your splitting done independently, will have a slight pessimistic bias. But that's it's not a problem. It's better to have the real model performing a bit better, actually. When the second assumption breaks down and the surrogate models are noticeably different from each other's, we say that the training is unstable, or these models are unstable. Unstable with respect to exchanging a few training cases. Because if you look, for example, at these 2 surrogate models and the samples they were, or the cases they were trained on, they only differ by exchanging case number 6 for case number 3. That's all the difference they had. So all the difference that we see here comes from replacing one case against another. This is a very direct measure of instability of the training procedure. And this, again, corresponds to the second point of view on the subsampling procedure that I mentioned before, where we see this as perturbed versions of the real sample. So what we can do here is we can either, and this works always for predictive models, we can either compare whether all the predictions we get for case 1 differ, all the predictions we get for case 2 differ, and so on and so forth. Or depending on the type of model, and this works much better for models where we have these explainability properties, where we really can grasp the meaning of the parameters of the model. we can then check the stability of these model parameters. In terms of our validation results, any kind of instability will cause additional variance uncertainty on our test results. And we can reduce this uncertainty by doing more repetitions. Does it happen actually? Yes, it does. This is an example that you can look up in my PhD thesis. In case you didn't recognize it, this is 40 times exactly the same measured image, in this case a hyperspectral image in the mid-infrared range, that was presented to 40 different such surrogate models in a very unstable situation. Blue would be the correct class, by the way. So we've already basically done this. How many cases do we need to train a good classifier? We have the rule of thumb. What I want to tell you is the answer is also called the learning curve. The learning curve tells you how the performance of the model evolves with increasing number of training cases. Now, as the last part of the validation here, let's have a step back and look at questions that you may ask that go further than just thinking of whether the sensitivity you observe in the cross-validation actually meets the specifications. And this is validation as opposed to mere verification. Verification results are part of the validation though. The first question is, does your model actually answer the right question? And this may sound very naive, that you need to reassess this, but I can assure you it is good to reassess, because very, very often you can't directly answer the application question. You need to go for a so-called surrogate. That is something that you think is almost as good. And then in validation, it's time to step back and think again whether your surrogate is actually as good as you thought in the beginning. Or where are the limits of this? Also, it's important to double check whether your model setup is actually appropriate for the situation. Or did you learn something meanwhile that tells you that, well, maybe this wasn't a classification problem at all. I've had tumor diagnosis data, grading. So those grades come according to the medical textbooks as 1, 2, 3, which sounds like an ordered type of class. But then it turned out that biology, unfortunately, did not read the textbook, and the tumors behave in a far more continuous fashion. So maybe regression model would have been more appropriate. There's also all kinds of different classification models, not only the ones that you have seen discussed this morning, as whether you do, let's say, random forest versus support vector machine, but there are more underlying scenarios, like all that you've been seeing this morning were so-called discriminative classifiers. They divide all the available input space exactly into the classes. But there are also classification systems where the classes can overlap and do not need to cover the whole space. So-called open world, closed world, and one class classifications. For regression, the scaling sometimes plays a role. Sometimes you should have transformed your variable in order to have an easier underlying structure in your data. Things like taking the logarithm, which is important in chemistry, because then you can rely on certain physical-chemical relationships that give you a chance of using a linear model, so you don't need to go for a highly complex nonlinear model, and in turn get either a better fit or need fewer cases? Do you have the correct kind of zero or base class or controls? What actually happens if some sample comes along that does not belong to any of the classes you've been modeling? Let's say you find, what was it in the morning, a Georgian written or a letter instead of a digit. What happens then? What does your classifier do in this case? Or your detector has a bloop and then something bad comes along. Did your data acquisition procedure cause bias possibly? We've had that in the checklist. What do you do with borderline cases? Are they extremely important maybe, or should they be excluded? Are there confounders, hidden factors that influence your system without you having access to them directly? What are the limits? And at this point, I'm sorry, the literature references did not properly expand. I will fix that before I upload the lecture. We can go even further and say we can perturb our data deliberately in order to check what this does with our model. This is done in deep learning, so would have probably been part of the lecture tomorrow, which we unfortunately don't have. But you can also do this with all kinds of instrument data. For example, I've been working with Raman spectroscopy, where the stability of the excitation laser is very important. So one possibility here is to either deliberately measure in a separate experiment what happens if the laser wavelength is not stable and test that kind of data. Or you go ahead and, because in this case, we know the physics very well, and we can simulate, we can distort the data accordingly as if the wavelength had changed, and could submit that kind of data to our model. But with that, let's stop the validation part and have a look into optimization. Martino already explained that hyperparameters are parameters that steer the behavior of our training algorithm. So for example, if we consider something like a principal component regression, that's a regression model that is done in the score space of a principal component. Score space you've seen this morning in the dimensionality reduction. If we have a regression type of problem, then we would expect a kind of maybe an elongated point cloud there instead of clusters. And this is available, ready to use in many different languages. But usually there's 2 or 3 things that you still need to decide. You need to decide typically whether the data should be centered and how. And you always need to decide how many and which of the principal components you're going to take, like Martino showed you this morning. And then, of course, we need training data. So if we come from the application side, we really wouldn't want to worry about this kind of number of principal components and centering and whatever. So we would like to have a training function where we put in the training data and then get out the model, and that's the final model and ready to use. But of course, it's not possible to program this so far because there's no sufficiently good heuristics that work on all kinds of data to fix those parameters without further inputs from the user, basically. And this link here is what hyperparameter optimization is about. And basically what is usually done follows the idea that we determine a sensible range search space for our hyperparameters. Then we build models that cover somehow all this search space. We measure the performance, that is, we do verification for them. And then, well, after verification, we know what the performance is, and then we can take the best. And this way we optimize the predictive performance. And there's a whole lot of numerical optimizers that are used. Most people or one, maybe the most fashionable or easiest one in machine learning is called exhaustive grid search. That is, we set up a hyperparameter grid and we calculate all those models, and when the calculations are done, we come back and see what's happened. When we say we measure the performance, that's exactly what we use validation data for. So all that we've been saying before about cross-validation, for example, applies here. Or we can do a single split, as you did in the morning. But careful. The moment we use our verification or validation results in order to select a model from a subset or do any kind of decision really on the modeling, that moment, this validation has really become part of the training process. And this means that possibly we can overfit on this validation data set by choosing hyperparameters that make the model overfit not only on the training data, but also on the validation data. And this is why we need yet another set of independent data that is independent from the whole training procedure, including the hyperparameters. And this is usually called test data. Now, I'm not very happy about this terminology, and it causes a whole lot of confusion. Like on cross-validated stack exchange, we have, I guess, every second week a question that is based on the confusion here. And this confusion comes from the fact that we take a set that is called validation set and use it to train, that is fit the hyperparameters. And after that, we do a validation, but we can't use the validation data to do the validation. So this is a whole lot of a mess. And therefore, I decided, because really all this in the dashed blue area is somehow involved with model training, or at least development or optimization, to call the second set here optimization set. Others call it also development set, which is also fine in my opinion. And I'm going to call the third set verification data in order to not have the confusion with what is called validation data in the other terminology. Okay. And really, for both types of splits, you can use all the techniques we've had before. You can do cross-validation. If you do cross-validation for both splits, it's called nested or double cross-validation, or you can do single splits if you like. That's up to you. Now, I've said before that we really want one training function that we present our training data to and then get the final model out, and then maybe do the verification. And so this function would get the blue dashed set of data for its training, and then can do its tuning internally. And if it does any kind of splitting for the tuning, that's its own business. And from outside that function, we don't need to worry. And this is actually a very powerful way of thinking about these things, because it makes things very easy. We only need, again, one train test split. And then inside, okay, we can have another, but it's wrapped away. So we don't ever need to worry about kind of the exact nesting. It will happen automatically if we wrap the hyperparameter tuning into its own function. And then from the outside, we're just talking training data and test data. Martino pointed already this morning that one of the important things that we optimize via the hyperparameters is model complexity. Because we have two types of difficulties that a model can have. It can be systematically off, and this happens if it is not sufficiently complex to follow the data. That will be the green line here. or it can be unstable. That is, it doesn't really know how to fix classification, the boundary, because there haven't been sufficient samples, so the sampling density is too low. And the total error, in consequence, will undergo some kind of U-shaped curve. And this is actually the case, and it has some kind of consequences, that this U-shape is not just an overall U-shape, but it has these components of instability here and under complexity on the other hand. These are some very easy simulation results. I'm not going to even show you how simple the simulation was. Sorry. The point here is we do have, well, the U-shape is not super easy to see, but we do see complexity somewhere here is probably sufficient, and we see of the gray range here basically that the instability means there is variance type uncertainty, noise. If we have this kind of noise on such a general behavior, and we then look for the optimum there, we will get a distribution, because sometimes it will accidentally happen that the optimum is up here instead of down here, or sometimes it will be also under complex. This is a histogram for that kind of situation here. What the strategy pick the best would have yielded. 4 is actually, in this case, the optimal complexity, which I know because I set up the simulation. There are very few models that are under complex, and a whole lot of models, actually the majority, that is too complex. And this is something to keep in mind. If you optimize and do not penalize instability, then you're likely to end up with a too complex model. And this is exactly the kind of overfitting also to the test set that I was mentioning. Here's a bit closer look to what we have. So I put box plots basically of the different runs of the simulation I did. And considering one run that had its optimum here at model complexity 10, which is far too much because it should be 4. Now, one way that is proposed in the elements of statistical learning of penalizing instability is that you can say, okay, we look here, optimum appears to be here. We then look at the variability that for our performance, for our figure of merit that we observe at this maximum complexity, go 1 standard deviation back, and then go for the least complex model that is better than this threshold, which would be 3, which would be slightly under complex, but given the fact that we had only comparably few samples here, that's certainly okay. To sum up the validation part, you need to think hard about your data, the model, and the application. You should do some kind of sample size planning. For the proportions and classification, you can do the calculation as a back of the envelope type from the required precision for your precision in the sense of width of the confidence interval for your validation results. Otherwise, you will need to do preliminary experiments, and that's actually anyways a sound experimental design choice to say, okay, I set up my experiment, if possible, in a way that I have an intermediate analysis after maybe 40% of the samples are through. So I have a chance to spot problems and adapt my whole procedure, measurement and modeling, rather than risk that at the end I'm there with a large data set and find out, like, let's say with the digits, that someone forgot to record who the writer were, and I can basically not do anything with that data set. I could train on that digits data set, no problem, but I would need to acquire another data set for testing with independent writers. At some point, of course, you do need independent testing, at least if you're going into serious business like medical diagnostics or things, space missions, whatever you do. Before that, repeated cross-validation out of Bootstrap are sound choices. You need to think hard how to get your splitting independent, though. And you should check the stability of the predictions and, if possible, also of the model parameters. Holdout and contrast is not very efficient. For the optimization, you need internal performance estimates plus then the outer independent validation. That means hyperparameter optimization always comes at the cost of rather large sample size requirements. I recommend that you follow this wrapping of the tuning function into of the tuning procedure into its own function, because it makes it easier to not make any mistakes in the splitting. You should also, during the optimization, check that the optimization results are stable, by the way. And I highly recommend using something like the one standard deviation rule, because our problem is overfitting. Under complexity is rarely the problem. For class data, classification data, Briar score has better variance properties and is thus also better in terms of not running such a high risk of overfitting in the hyperparameter tune. Now, with that, unfortunately, I'm running quite late. So we have another 20 minutes left. I do have examples for hyperparameter tuning, which would maybe take something like half an hour. I also have regression, and I even have an example for that. So maybe the question is to the organizers, how do we proceed? Should I rather skip the example for the hyperparameter optimization and do regression including example, or do we want hyperparameter optimization and skip regression, or do we run late? Which would be fine with me.
I think we can run a little late.
Okay, thank you. So then let's have a look at hyperparameter optimization, and I'm again doing this. I'll take the digits data set that you know from the morning. So we have loaded it already. And in the morning, we did a train test split. We're going to do now cross-validation immediately combined with a grid search. So we need to import from scikit-learn the SVM. That is the classifier. And we need also from the model selection, the grid search cross-validation. And you've already been experimenting this morning with various values for C. I'm going to use a couple of them here now as well. And also a bunch of different gamma values. And they together define for us a hyperparameter search space, which I put into a grid definition. Where we have the parameter C, which takes the values we've reserved for the grid up here. And we have the parameter gamma, where we enter the gamma values we had here. And we need a third parameter, which is the kernel, which I'm not going to optimize. I'll keep that with the Gaussian kernel that you've already been experimenting with. But I do not want to add yet another level of wrapper function for reasons of being fast. And now we set up the grid search, which is done by the grid search CV function. Maybe fivefold. Again, I'm sorry. I would have preferred to be able here to say that we split by writer, but unfortunately we can't do it. So we are going to pretend all the digits were written by different persons. We need an estimator. Estimator is our support vector machine. And we need the parameter grid. And what this so what else do we have? Sorry. So with this grid search CV, we now initialize basically the CV. That is, we define what's going to be done, but the actual fitting is done by fit, where we present the training data. And oh, I'm sorry, I should have set up quickly what we did in the morning, basically. This is not. And that is, search dot fit, and we need from our data the training data is actually, sorry, in digits inside the data, and labels train are in digits target. So, and then I use here data train and labels train, and you have seen here that instead of the outer split, the train test split in the morning, I now took the whole data set here. And this is because for time reasons, I'll skip the outer part where we check against overfitting, and we'll show you only the inner part of what happens inside the the wrapped auto-tuning function, and leave that to you to encapsulate this into the auto-tuned function, training function, and then do an outer either cross-validation or single split. I think I went wrong. And I should have said that this is this takes now a little bit, because what happens now is actually that 5 surrogate models are computed for each of the 30 combination, but each of the 25 combinations of gamma and C. So in the end, we'll have here 125 models that have been computed. Meanwhile, I prepare that we can then have a look. There we go. And the results. And so we get back here a whole lot of information, including the time it took to fit. And what is interesting for us is down here, we get the averages and the standard deviation of the different folds for the score that we were asking for, but we didn't specify it, so it took the default, which is the accuracy. So, and then maybe it will be good to plot this to get an overview of what's going on here. Search the results, test score, and I'll immediately reshape this because this is a vector basically here, but we actually had a grid, and this should be reshaped with the length of C and gamma. So, yes, we got it reshaped here, and we can no. Similar, we can look into the standard deviation, which is stored up here next to the average. That's the average across the fold and the standard deviation across the fold. Unfortunately, those standard deviations mix two sources of variance here. Part of our variance is coming from the fact that we have only a finite number of cases that we test, and the other part is instability. And it is actually possible to separate those two, but not in this easy example here. So this will require substantially more work. So let's look what we have here. So our average, we have a region here where the accuracy is thought to be 97%-ish, but actually we went far enough away with our parameter grid that accuracy really drops down here. And we can also see that the standard deviation, which in this case must be roughly instability because the cases are always the same in the cross-validation in the end, is very low here but yet substantially higher here. And maybe to quickly finish this example, it's nevertheless good to plot it. Not plot lib. And so we can plot the mean. So we see here, here's the region of bad performance, and down here is a region where performance is really much, much better, as we know, close to ideal. And one thing we can also see here is it's not just that we can say, oh, take the smallest gamma or the smallest cost. It's like a more complex decision if we have to decide inside this region here. We can similar, I'll do that very quickly. Have a look at our standard deviation here, and we see that the picture here is actually has quite a different pattern. So we have a region here where we see high standard deviation with an intermediate, let's say, average. And this, without having looked closer into this, I would, my first guess here would be that the fact that we have intermediate performance here, this will always cause higher variance. That's mathematically tied, basically. So this may be the cause for this here. But up here, performance is bad, and instability, standard deviation is high. So this is where things really get unstable. And so we have this region here where things are very stable, but it's not useful because also performance is bad. We have a region where performance is good, and within this region, we would say that probably we want to go for hyperparameters here, maybe up here, because of the low complexity constraint that we'd like to have, and potential overfitting also in our CV test sets, because we use them for selection here. So this was a very rushed example on the hyperparameter optimization. With that, let's do a little bit of regression at least. Regression is really much easier than classification, because what we do want to model is a metric variable depending on some other, usually also metric variables. In chemistry, it's important somehow to distinguish which way we set up the regression. There's actually discussion about that. This is called ordinary or classical regression versus inverse regression. And the question is which way the model works. Pretty much all the machine learning models we use do what is called inverse regression. They predict y directly from x. In terms of chemistry, this would be, for example, some concentration as a function of the intensity we measure. And this is why we call it inverse regression, because the causality actually of the physics behind our measurement is exactly the other way around. We would never say we observe a concentration because there's some intensity we measure. We would always say, well, because we have a concentration, we do measure some intensity of a signal. That's the model that ordinary regression uses. And then we solve back there for the concentration. From a statistical point of view, this corresponds to the ordinary regression, saying that the measurement error is basically concentrated on y, or the intensity. That is my measurement instrument has a lot of noise, but I know the concentration very well. Whereas for the inverse regression, we basically say the error is on the concentration, and my instrument has hardly any noise. After looking a couple of years after MATLAB practicum with students, I'm totally convinced now that inverse regression is the way to go. No, there are actually considerations that can lead to setting it up this way or the other way. The take-home message is that inverse regression is good, is what we need actually when we want to predict Y values. If that's the usual thing in machine learning to do, then we will usually use inverse regression. On the other hand, ordinary regression is better at estimating the parameters of the calibration line. So if the parameter we're actually interested in happens to be, for example, the slope of the calibration line, then we're better off doing a classical regression. Now, the regression models, also many of the calibration models, are often written down, noted, or linear regression in this matrix form. So we have a matrix of dependent variables y, which is modeled as x, our inputs, our features, times, that's matrix multiplication, some kind of coefficient matrix. We would say here that n is the number of cases we have, m is the number of columns in our y, that's the number of independent things we want to predict here for each of our cases. And then our measurement is possibly multivariate with p variates or features. And then the coefficients have to be of this shape and size. So in the univariate case, things are very easy. Y is univariate, for example, like here. That's just a column vector. X is also just a column vector. We would usually say that B is a slope and an offset. Unfortunately, we don't have an offset here. We can either write it with an offset or do a trick that I'm going to show you in 2 slides that we don't need the offset. But the general idea is that we can relate those two together. And this is called a linear model. And it's also linear model in scikits, sorry. So I will go on with the notebook and switch to regression. And I'll set up a toy function basically here, which is our true underlying function. And it's gonna be nothing very complicated. It's gonna be, let's say, some cosinus. 1.5 pi x, and of course I'm not sure whether I imported NumPy already. Maybe better to write it anyways. And I'm also going to set up FineGrid in order to have support for plotting the functions, which I do on an equi-spaced basis between 0 and 1. Okay, would be good to actually type the equal sign. Okay, here we go. And so I'm gonna produce data for us here by sampling this function and putting some kind of noise, random noise on it. And in order to ensure, just for the sake of the tutorial here, that we all see the same, I'm going to fix the random seed to 0. Not very special choice. Let's say we want to sample 30 points, and then say we want to have an X that's somehow sampled uniform, random, better sorted maybe. How does that look? This is what we have. And of course, we need a Y that kind of belongs to it. So if you want to have a function evaluated on X, and then we put some, oops, sorry, X plus some random numbers. We need the same length. I guess we can scale down the noise. Okay. And again, we're also gonna need some test data sets. And I should have put my random seed here, so the seed is actually executed whenever I run this cell of the Jupyter notebook. And we can make it same length, but it's important that my test evaluates the true underlying function at X test. Okay. Now let's have a look how this data actually looks. Got something like this. Let's check how our test data looks as well. And make this mainly red. Okay, here we go. And although we can have a reasonable guess how the true function looks, because we did not add that much noise, that's maybe good to plot the true function as well, which means that we need to use our fine grid support and evaluate our true function on this fine grid. And here is our true underlying function. So now is where the actual fitting starts. You're gonna need to set up a pipeline, because if we have a look at this function and our data, there's really no way how we're gonna approximate this with a linear function. But you may remember, and because let's say we had data, sometimes you know that cosine type of function, you can do a series, how's it called in English? Series expansion, probably, where you have the even terms of a polynomial. And this means that a polynomial should be working reasonably well for what we are doing here. To go back to our linear regression, that would be a straight line. And now the first general way how linear models can be expanded, which is actually written here already, is that we can go multivariate. That is, we have, instead of a single x column, we have several x columns that are more or less correlated with our y, and we want to fit coefficients accordingly. Now, we can have a special case of such a multivariate x, which is actually polynomial of a univariate x. And that is, instead of having different features that have been measured, let's say, by different channels of an instrument, we use now x and different powers of x. So, for example, we can do a regression with a polynomial function of second order, second degree polynomial here, by having 3 columns with the powers 0, 1, that's the usual x, and squared. And the 0 is actually the trick I've been referring to before, because x to the power of 0 is always 1. We get here a column that is always 1, and this will make the corresponding coefficient in our model be an offset. So really, we do not need to have an additional offset for our linear model, which is described by this matrix multiplication, if we include an offset term this way. So this is really equivalent. And this is what we're going to do. So we're going to set up what is called a pipeline. And this pipeline consists of first producing this polynomial and then going into a linear regression. And the pipeline is a scikit-learn pipeline. So we import pipeline. Okay. Then we need to import a few more things. We need to import, do I need to import pre-processing actually? Yes, I do. Oops, sorry. We need from pre-processing polynomial features, which do produce those polynomials, which is one way of what is more in general a feature generation. We will also need a linear model, which is in our case a regression model. What else do we need? We need metric in order to find out how well our model does. Main squared error is totally appropriate for that. And finally, because I like to have my root mean squared error, so we're on the same scale here and not squared. So we're going to need somehow a square root which we get from math. Now, the pipeline that we're going to set up will consist of polynomial features, which we need to define. Polynomial features. They are produced by function polynomial features. And well, we'll start with a degree of 2 for the moment. So this is actually where we enter our hyperparameters. And I'm not going to set up a proper auto tuning here. We're going to do the tune by grad student, like at the end of the morning session. We need to specify whether a bias term should be included. We're not going to need that. It's not going to help. Oh, sorry. But we can check it later on. And so we can use the polynomial features here. And then we need linear regression, for which we use a plain linear regression. Is that correct? No, of course not. I think I forgot to tell him here. Okay. And we better give a name to our pipeline. And now we can start the fitting again. You start to see the pattern. This is not that different from how the setup of the grid search CV was. One thing we need to keep in mind here is because our X so far is not the column vector, we need to produce one. And that is, we need to set it up this way. Let's check this. Yes. Okay, and of course we need to hand over our Y. And well, now we have a fitted model, so we can start and predict. Sorry, I call the model pipeline. So we need to predict the pipeline, and we can give, of course, new data, for example, our test data set. And again, we need to make sure we have a column vector here. We get our predictions. and maybe just check what happened here. I'll just copy all of them maybe. So we start with the old picture, and in addition to the actual test results, which are in red, we put the predicted test results maybe let's do that in orange. Okay. We can also, similar to what we had here, use our fine grid, but not the true function now, but do a prediction. So we get actually the function that was fitted. This gives us a better overview. Okay, so here in orange, we see very clearly our second degree polynomial now. And I'm gonna, before I'm gonna start playing around with the degree. Oh, there's a question on the Slack, whether sklearn metrics library in sklearn is, yes, it's in sklearn, and it's, well, it's a collection. It gives you access to a whole bunch of different metrics, like root mean squared error. So let's look at the mean squared error, or the root mean squared error. And the okay. So these metrics again work by comparing the prediction with the reference value, which is our y test here. What we can do now, basically, and I'm gonna enlarge a little bit so that we have everything here. We can do the correct student tuning as before. So we can see linear model is not gonna help at all. Also has a really large error, of course. Probability we had before, so we're at 0.23 with the root mean squared error. Third degree helps substantially. If we go further, it's not that much of an improvement anymore. So we would probably in the end say that somewhere here, probably a third order polynomial is where we should not go further based on the data we have. But of course we can in principle, and then you will see what actually happens if we overfit here, which is probably what you've seen in your math lectures before. That is, if the polynomial degree of freedom approaches the number of data points we have, that's 2 data points per degree of freedom here, then of course it starts getting super squiggly, and well, things get out of control basically. We can maybe make a limit on the y-axis, say minus 1.522 or something like that. Yeah, so we can still see our data and how this polynomial gets like totally out of control, and we have these points here actually driving our mean squared error. And I think with a view to time, I would leave it like this and rather have a look at what kind of questions come up.
There is an additional question on which function you can use rather than polynomials.
Well, here at so there's a bunch of things you can do within the framework of linear regression. Although I think polynomials are possibly the most important set of such basis functions, but you can have other basis functions as well. What you can also do is that you start transformations. So these here are transformations on your x. And in addition, what you can do is you can have transformations both on x and on y, and sometimes this helps as well. And this leads into a whole new family of models, which are called generalized linear models. And then you can further do different generalization where you start with different kind of basis functions and put them piecewise together, and you go into spline regression with that. And then you can leave the field of the let's say the field of those models that still have linear in their name. And by the way, these are called linear not because they're a straight line. This polynomial would be called a linear model as well, because it behaves linear in the coefficients still. Then you can go to the truly nonlinear functions, and then you have pretty much, I would say, pretty much the whole zoo of models that you have available in classification usually they have also some kind of equivalent in regression. You can do neural networks for classification or regression. You can have random forests for classification or regression. You can have support vector machines for classification or regression. You can go for, that I forgot, that should have been mentioned maybe, if you have highly multivariate data, there are different kind of latent factor models. For example, you do a PCA first and then a linear model in that. That's kind of going the other way around, reducing complexity when you have a large number of features already. So we have some like these polynomial approaches or other basis functions that would allow to basically expand the number of features or generate new features. And then we have other functions, and in case you have a large set of features in a highly multivariate setup, where you want to combine features that are anyways correlated into a smaller number of features. That would be something like principal component analysis or partial least squares regression. And you can even combine them. So this is like there's a whole zoo of things. I hope this did, well, maybe not answer, but at least open the field of study.
Yeah, thanks. Okay, I don't see any other question in the chat. I suppose you will also provide the notebook you just edited after
yes.
the lecture.
So I uploaded in the lunch break two notebooks, one with the validation and optimization part example, and one here with the regression example. The regression one has a tiny little bit more than what I've been showing here. So maybe people would be more interested in those, but I can also upload the notebook as it was, of course.
Yeah, great, thanks.
So, well, I guess I better save it then, right? As I'm happy to answer further questions. Also, if people email me, I don't know whether the emails are distributed. And I'm sorry if after lunch break on a hot day, I kind of overwhelmed everyone with this.
No, thank you very much, Claudia. Amazing. And yes, sorry, Thomas also was mentioned.
Yeah.
I don't see more developments in the chat, but regarding what you mentioned about the contacts, I don't know if if you would like to share it there on the Slack. So obviously, it's at least limited to the people who is really participating in the school.
Yeah, you can have the slides.
And
but I have not yet uploaded them anywhere.
Yes, sure. We will reorder obviously the classes and in the website that we have for this. In this case, yes, I can again just to thank you again for the presentation, for the demos. Usually very challenging, especially it's always a challenge to be sure that everything's working. So thank you, and thank you everybody that have been obviously.
I would like to thank Benson, who has been helping to prepare things as well, and has kind of held up the Slack side of questions. So thank you.
So yes, I don't have too much to say, but I guess Thomas will mention some final details, and at least from my side, I just want to say thank you to everybody, and hopefully we will meet at some point in person, even if it's not together during this path, that many of you will find you in the laboratory and the different laboratory that you saw all these tutors around the world and say, hey, I was in the school in Annecy 2-3 years ago. That will be very cool if you do that, guys. And thanks again.
Yeah.
Yes, thank you, Arturo. Thank you, Claudia, of course, for the lecture. And
well, thank you, everyone, for keeping around that late, right?
Well, I'd like to thank everybody who participated. Of course, all the tutors who dedicated time and effort to prepare the lectures, all who helped to organize the school. Thank you very much. And of course, thank you to all the participants who followed during these 2 weeks and were quite active in the chat. I think we had a very nice exchange during this call. So as you saw, unfortunately, tomorrow we won't have the last lecture. That's a bit unfortunate. I know that some of you were waiting for that lecture on deep learning, but we will provide some material and also point you to some other lectures online that you may find useful to learn about deep learning. I have already created a post where we will gather some additional content that we discussed during the school on the portal. I also offered the possibility, well, thanks to Benson ID, to offer the time tomorrow to some participants to present something, to present maybe their work or some project, data project or Python project that they are working on. I had an answer from Ricardo, but I'm not sure he will be ready by tomorrow. Watch out so for announcement. Maybe we'll have a short presentation tomorrow if you can still connect. And yeah, I will send a lot of information after this, after the school by tomorrow, I think, for you to complete some surveys, to give us some feedback, and to have some more information to close the school. So yeah, I think that's it. I won't overwhelm you with information right now. I will send them by text, of course. So thanks again, everybody. And yeah, see you around, I hope, in person next time. Bye-bye.